All right. Good morning, everyone. Thank you so much for the invitation. It's my great honor and pleasure to come here and see many of the friends I've met in Bangalore and all over the world. I'm going to spend the next hour on a new internet architecture that we've been researching called Scion. This was in conjunction, of course, with my research groups at CMU as well as at ETH Zurich. And I'll introduce the people as we're going on through the talk. So I'll start right away. If you think about a picture for the internet, you may think about the pyramids. It's a monumental structure that has stood the test of time and cannot be easily changed or moved. But the better you know the internet, the more you're going to maybe change the picture that you have of it. And so in this talk, I hope to convince you that the internet more resembles this structure with these 4 pillars. And we've talked about the 4 pillars before. If one breaks, maybe the whole structure collapses. And so I believe today's internet more resembles this structure here, which is ancient, unstable, and quite brittle. I'm going to talk about 4 different aspects that are important in today's internet: control, transparency, availability, and trust, and argue that we don't really have any of these four properties today. Let me start out with trust. In the early days of the internet, everyone knew pretty much everyone else, and there was a lot of trust among people who ran the network. There's a very nice talk by Danny Hillis. It's a TED talk. You can easily watch it online, and it's called "The Internet Could Crash. We Need a Plan B." And he gives a nice anecdote where, in the early days, there was a small booklet which contained all the email addresses and numbers, phone numbers of people who were on the internet. So everybody pretty much knew everyone else, and people really could trust each other. Unfortunately, today, this is not the case anymore. Right? We have the internet has expanded to the whole world, and clearly we cannot quite trust everyone anymore who's on the network. So, in fact, the heterogeneity of the global environment has made authentication infrastructures very difficult. And so in this context, important are authentication of routing messages as well as DNS replies or TLS certificates. And today, we're mostly relying on 2 different models for authenticating entities in today's network. One is called the monopoly model, and the other one, the oligarchy model. So let's look at each one in turn. In the monopoly model, we have a single root of trust, for example, a public key, that is used globally to authenticate various entities. And examples of this include RPKI, which is used in BGPsec, so that's the resource public infrastructure, or also DNSSEC, which fundamentally relies on just a very small number, or one public key that is used to authenticate DNS responses. And so there are a lot of problems if you have a single key that the whole world relies on. The first problem is that the whole world has to agree who is holding this key, right? So as Swiss often joke, the Swiss could hold that key, right? Everybody trusts Switzerland, but that's of course not really the case, right? There are plenty of people who wouldn't trust Switzerland. So, moreover, there is a single point of failure, right? If the single public key or the single private key that corresponds to this public key is being revealed, then obviously the whole infrastructure and all the security properties are lost. Also, current systems have quite inefficient revocation and update mechanisms, which complicate running these infrastructures. The oligarchy model is not much better, unfortunately. In the oligarchy model, instead of having one single key that is trusted, we have a lot of different keys. And if any of the trusted keys certifies any entity, that entity is trusted. So today's TLS, public infrastructure, relies on this oligarchy model. And there are literally 1,500 different keys that can sign certificates. And so if any certificate that is signed by any of these roots of trust then that certificate is being trusted. And so obviously, you look at this, and obviously there are a lot of problems with this approach. So again, it has a single point of failure, but this time a lot of these single points of failures. If any of these 1,500 private keys is being compromised, which means somebody may obtain the corresponding private key, then they can sign arbitrary certificates for arbitrary entities on the internet. Also, the revocation and updating is not very well done. If you look at the case of DigiNotar, who got their private key compromised, then you know that in order to remove that key from the browsers, an operating system update or a browser update was required. And that obviously can take on the order of weeks until a majority of users has really updated their operating systems or browsers. And so revocation and updating of these roots of trust is very complicated. So the oligarchy model, unfortunately, is not much better. So how can we get to higher levels of assurance in today's internet? And so one proposed approach I'm going to make in today's talk is the approach of isolation domains. And so the observation is that if you have a smaller area of the internet, a subset of the internet, that these people could agree on a root of trust and then form an isolation domain with that root of trust. And so we would then authenticate entities within isolation domains, and this would also provide some choice for users as well as corporations to select which isolation domain they want to be active in. And then you can make use of modern approaches to public infrastructures like certificate transparency by Google, or a proposal that we've made called AKI, or a more recent one called ARPKey. And they can also operate, and they would also greatly benefit from having these isolation domains. A challenge here, though, would be to have global verifiability, but unfortunately I won't have enough time today to also go into these details. But I just want to propose this mechanism as a generic approach, and I'll talk more about it in the later part of this talk. Let me next talk about the problem of control. And anyone knows control is an important aspect of running a family or a company or any research group, or also the internet. So the question is, who controls the internet? And obviously, a lot of countries desire more control. In Europe, we've had a famous case where Angela Merkel and Germany proposed the notion of a Schengen net, or a European network, which would exclude the UK, for example. So continental EU network, or also other countries like Brazil, China, Russia, specifically desire more autonomy. And also isolation domains I've mentioned earlier can help here. But a more technical aspect of control includes the actual control of networking paths. And before I get into details of this networking control, let me briefly talk about BGP, the Border Gateway Protocol, which is the main routing protocol used in today's internet. It's actually the interdomain routing protocol used in today's internet. Actually, I'll briefly want to mention a parenthesis, which is, as a lot of people here are aware of SDN, right? And there's also an SDN panel, SDN workshops. But in today's talk, I mostly talk about interdomain communication. SDN is used in intradomain, so within a single domain. And so what I'm discussing today is not in conflict with SDN. SDN essentially will be used inside domains, but I'm, in this talk, mostly addressing the interdomain aspects. How can we connect the different domains together? And BGP is the protocol used to provide routing for interdomain networks. So each circle here in this slide would correspond to an autonomous system or an autonomous domain, which essentially could be like an ISP or a university or a corporation. Each, like our sponsors here, Cisco, would be one of these circles, same as Microsoft or Google, would correspond to one or maybe multiple of these circles. So the way BGP operates is that each autonomous system that owns a certain IP address space announces this space using a BGP announcement. And so this BGP update message, as it's called, then traverses the whole network, and essentially the packets destined for this destination would traverse these arrows in reverse to reach the destination point. What's important about this approach in this talk is that every address space, every AS that wants to announce an address space, floods this message to the whole internet. Right? So essentially, if you have n domains, you have n floods that traverse the whole network. Now, the important question I want to get back to is who actually controls these internet paths? And the current BGP protocol is very limited in the amount of control it permits for these networking paths. So here I show an example. We have the lower AS shown in black that disseminates its IP address space, its IP prefix. And let's say the prefix traverses these two paths, the blue path and the red path. And now it arrives at this upper black AD. And this AD now really decides how traffic destined for the other AD will flow, if it flows across the blue path or the red path. There is no way that the lower destination can actually influence how it wants to receive this traffic. Right? So it's really out of the control. Even its own ISP, which cannot really decide whether the blue path or the red path is going to be used. And so there's very little control that destinations have in today's internet. Also, recently we've seen various attacks that demonstrate the lack of control we have in today's internet, also the lack of transparency. And I'll get back to this in a couple of slides as well. But here I'll show these attacks that the corporation called Renesys has nicely documented. And it may be a little bit hard to see, but you see a map of US and Europe, which shows a networking path from Guadalajara in Mexico to Washington, D.C. And usually, this green path would be followed going via McAllen, Texas, Monroe, LA, to Washington, D.C. But what in fact is happening is it's presumably a corporation in Belarus, in Minsk, that has hijacked this communication and has redirected it to go via London, Moscow, and Minsk, and Frankfurt, and then back to the US. So this is nicely documented by Renesys, and they document a lot of these cases. Here's another one going from Denver to Denver. And strangely enough, this traffic actually goes through Dallas and Kansas City when it's correct. But in this case, it actually, again, goes via London and then via Iceland. Also, this packet from New York to LA goes via Moscow and Belarus. And in this example here, a packet from Chicago to Tehran crosses the Atlantic 3 times. So it goes 3 times across the Atlantic. So you may say, well, you know, Adrian is a security guy, and these security guys, they always try to scare us, right? They always have these examples. They always do this. But actually, my research group also looked at this, and the students noticed that a large fraction of traffic that should have stayed inside the US actually went via Europe. And I kept telling them, I think you've made a measurement error. There must be something wrong. Because they came up with 5 to 10% of the traffic actually went via London and via various European countries, which shouldn't have, because it's within the US traffic. And so I said, well, maybe an autonomous domain could have had an operation also in Europe, and so you shouldn't count it for Europe because the traffic actually didn't flow through Europe. But they kept coming back and they kept saying, no, we're right. But we never really followed up. But it's quite common that this is really happening today. What's interesting for these examples is if the destination performs a trace route, they actually don't see this path, because this is only for one direction. So as the victim here, in this case, if you do a trace route from Tehran, you actually don't see this happening. So I recommend you to look at the Renesys report documenting these issues. But let's come back to the actual question of this talk, which is who should actually control internet paths? And you could argue, of course, ISPs need to control paths, but then who else should control paths? Should the receiver also have some control over networking paths? And so there are 2 extreme cases without any endpoint control, what we have today. or very limited endpoint control, all the way to complete endpoint control, which would be corresponding to source routing, where the source selects every hop. But both of these extreme cases actually have many issues and many problems. And what I'm proposing today is to provide a more limited form of endpoint control to have kind of be in the sweet spot between no control and full control, which provides very nice properties, as I can also discuss in this talk today. So let's now look next at transparency and availability. So in terms of transparency, we'd like to obtain some strong guarantees that a network packet actually takes the path that the sender intends. But in today's infrastructure, it's actually impossible to gain strong assurance of the path of the packet. You could look at all the BGP updates in the network, but in fact, the routing table may be inconsistent with the actual BGP updates. You can never achieve strong assurance that the packet is actually going along the path that you think it's going. Moreover, because the routing table update is asynchronous, it could be that even though you have perfect information about the network, as you're sending the packet, some router updates the routing table, and your packet will not go along the path that you thought it would go when you sent it. And so it's truly impossible today to gain strong assurance how your packets will flow through the network. And what we're proposing is an approach called packet carried state. It's not source routing. It's really the network would provide some network paths to the end hosts that then embed these paths into the network packet. So in this example here, this black AD sends a network packet that specifies the sequence of autonomous domains it traverses. And so this packet would traverse the red, green, and blue ADs. And so the source has some level of assurance that the packet really goes along this path. So transparency also has to do with trust. Essentially, who needs to be trusted for a given network operation? And this is also difficult to achieve today. If you take all the network aspects into account, you'd have to know, if you ask the question, which entities need to be trusted for this packet to reach its destination? There are a wide variety of BGP entities with respect to RPKI that need to be trusted, and then also with respect to DNS, if you use secure DNS, and finally also with respect to TLS. And so it can be quite difficult to really figure out what are all the entities that do need to be trusted for this communication. So finally, let's look at availability. And in today's internet, we actually have quite poor availability. If you look at a very well-connected entity, you get about 3/9 of availability, which corresponds to about 1.5 minutes per day of unavailability. And this was documented by Katz-Bassett et al. At SIGCOMM 2012. What's interesting is there are a lot of short-lived outages due to BGP route changes. Whenever BGP changes its path, in some cases, there's a short cycle that is formed in the network that is resolved within a second or two. But within that second, the packets go around the cycle and cannot reach a destination. And this also was documented by a paper by Dina Khattabi and her group at MIT, where they looked at outages or lower voice quality in communication. That was oftentimes corresponding to a BGP route change whenever there was a disruption in the voice signal. What's very important, though, in this context are also route convergence delays. In fact, the BGP sometimes has quite poor convergence, even though we use route flap dampening and all these mechanisms. And so there are some cases where, for example, there was an earthquake in Taiwan when in Southeast Asia, the whole routing was down for 30 minutes. So even though correct network paths existed, BGP took 30 minutes to reconverge. And this wasn't even an attack, right? It was just a benign, an earthquake that happened. It's not a actively malicious attack that happened. And even so, in Southeast Asia, we had routing disruptions for 30 minutes. So you may wonder, why are we using such a protocol still today that has these really poor convergence properties? There are also many examples of outages due to misconfigurations, and of course, outages due to attacks. And if you doubt what I'm saying, I recommend you to sign up to the NANOC mailing list, and then you see pretty much every day somebody noticing some outage somewhere, and they need to resolve it via the mailing list because they don't quite know whom to discuss this with to resolve the outage. And so some people here may sit and say, well, 10 seconds a day isn't really that bad, right? Why do we need a new network? So why do we need higher levels of availability? But of course, for a lot of applications, I'm going to argue, we do want high reliability. And today, Amazon spends a lot of money to obtain 4 nines of availability for their data centers. We've had about 5 nines of availability for the telephone network, and an IBM mainframe achieves about 6 nines of reliability. So it's possible, but today's internet, you'd have to spend millions just to get this connectivity that the Amazon data centers are using to get to 4 nines of availability. And so even 4 nines, I claim, are insufficient. For example, if you have critical infrastructure command and control, like air traffic control or smart grid control that uses the internet, you would like to have higher levels of availability. Also, of course, if you have an internet-based business, you'd like to have high availability, or if you perform financial trading or transactions, or telemedicine, you'd like to have high availability. And so the approach I'm going to propose in today's talk is to actually replace the BGP protocol. And so you may say, well, why don't we use BGP-SEC? That solves all our problems. That's what a lot of people are saying. But if you look at the details of BGP-SEC, it actually also introduces a lot of additional problems. There's trust issues, the single root of trust. There are control issues. There's still no endpoint control. There's still no transparency where the sender can obtain strong assurance of their path. And the availability is actually lower unless there are attacks, of course. But the availability is lower because the convergence time actually increases in BGP-SEC. And BGP-SEC still is susceptible to some attacks and as well as misconfigurations. So what I'm also proposing here is really we have to take a revolutionary change to really resolve the problems I've been talking about. Evolutionary changes are not enough. And the reason is some problems are really fundamental. Like the convergence problem in BGP, if you want to resolve these convergence issues, you need to have a protocol that doesn't use this iterative process to converge. And that's so intrinsic to BGP that you cannot solve the convergence until unless you really change the protocol. Also, a revolutionary change is quite desirable because when you start from scratch, you can really do things right based on the mechanisms and lessons that we've learned over the last 40 years. 40 years. So also what's surprising is that a revolutionary change is actually quite easy. And the reason is, inside autonomous domains, we don't really need to change anything, right? We can use SDN or we can use any current protocol. To use a new protocol, all we need to do is change a few of the edge routers, and pretty much that's it. I'll come back to this at the end of the talk. And this was a big surprise to us, and that's why some ISPs already are trying to use what I'm going to present today. It's actually quite easy to deploy and run simultaneously with current BGP. There have been a lot of proposed future internet architectures, and for example, I think Dipankar is giving a talk here about mobility first. And so I'm also part of the XIA team at CMU, which are some of these new architectures that are proposed. But what I want to focus on in this talk is really a security-focused architecture. How can we design a network architecture that provides maximum reliability, and systems and proposals like mobility first or XIA or even NDN or CCNX, they can make use of the techniques that I'm going to present today. So what I'm proposing today can be used for the basic point-to-point communication of all these other architectures. And so I'm going to talk about the SCION project. SCION stands for Scalability, Control, and Isolation on next generation networks. And we have the main team here shown in red, but there are a lot of other collaborators and colleagues who've worked on this since we started in 2010, actually 2009, on this project. The main architectural design goals in Scion are the following. So first of all, we want to achieve very high availability. So even if there are malicious parties in the network, malicious autonomous domains, or malicious routers, we want to provide high availability as long as an adversary-free path exists. So this is really the highest and most important design goal that we have. Next, we want to achieve secure entity authentication that really scales to a global heterogeneous environment and also provide flexible trust. So provide choices for users whom they want to trust and make sure that they can operate and really communicate with anyone else with their roots of trust that they select. We want to also provide a lot of transparency, so it's very clear to the sender and receivers what is happening to their packets and who needs to be relied upon for the operation, for the communication. Then next, we want to achieve balance control amongst path control amongst ISP senders and receivers. And of course, the network needs to be scalable, efficient, as well as flexible. So let me directly now explain Scion in more detail. So first of all, we have this notion of isolation domains, which essentially is the notion of having different entities agree on whom they trust in the network and whom they want to connect to. And then we run this, we establish this isolation domain. It's still an open issue exactly how to best structure these isolation domains. But one possible partition is along geographic regions, so that within one region, we assume that people could, say within India, people could agree on the root of trust and then run an isolation domain within India. This is how this would look like. We have different isolation domains here, and we see in one the actual structure. Of course, all the isolation domains are connected to each other. So the idea would be that the isolation domains are only visible with respect to the control plane of the network, so only within routing. Within the actual sending, everything looks the same as in today's internet. Right? You can still communicate with anyone you want to. It's just the architecture provides isolation for the control plane, but transparency for the data plane. So when you actually send a packet, you know exactly which isolation domains your packet traverses. Now, this is an important slide because it shows how the routing actually works within an isolation domain in Scion. And the way it operates is that we have the isolation domain core, which here shows 3 black ADs, which would be the ADs that manage this isolation domain. So this would be the top level autonomous domains within this isolation domain. And what they do periodically, they send out a beacon message that simply traverses the network. And these beacon messages trace the path they've taken. So essentially, after a single flood, every destination knows several paths how to reach this isolation domain core. So in this example here, the red and blue autonomous domains obtain 2 paths, and the green autonomous domain obtains 4 different paths how to communicate with this isolation domain core. And even after this single flood, everybody can already communicate now with the isolation domain. So next, the destination selects how they want to be reached. So for example, all these ADs would select which paths they want others to use to communicate with them. And they upload these paths to a path server in the ISD core. Now, if the blue, a node inside the blue AD wants to communicate with a node inside the green AD, what they do is they download the paths that the green AD has uploaded and now select one of these paths. And they combine a blue path with a green path. And in this example here, there's even a shortcut. So there's a shortcut to go from one of the blue paths directly to the green destination without going through the ISD core. And so actually, what the network packets will contain this AD level path in the packet header, so the packet directly then traverses this black path. Now, this approach I've presented is actually very, very simple. The actual flooding stage is extremely efficient because even if you have a huge network with a lot of destinations, there's only a single flood that needs to occur, and every entity obtains their set of paths. Also, there's no iterative process involved, so there's no convergence that needs to occur, right? The network immediately converges essentially. The different isolation domains also isolate these beacon messages, so the control plane achieves a nice level of isolation. And also another advantage is that the forwarding packet contains the path, and so there's no forwarding table at routers anymore that's necessary. So the forwarding actually even is faster than in today's internet because no routing table has to be looked at. Also, the forwarding achieves transparency because the source knows exactly how the packet is going to flow, and also the source can use multipath forwarding and use multiple paths at the same time to communicate with the destinations. The route control also is very balanced because ISPs can select which paths they want to re-announce. They control the beacon messages. Then the destination controls how it wants to be reached. And then the source, again, makes a choice how the packet actually reaches the destination. So it's really quite a nice level of control. However, nobody has complete path control. So it's not source routing. It's called a source-selected route. Right. Now, the cryptographic aspects, of course, are also important. These messages, these path construction beacons to find paths have to be protected. And also the forwarding information has to be cryptographically protected. Now, unfortunately, I don't have too much time to go into the details. What I'll briefly show is that we're adding digital signatures and a message authentication code to each packet. Now, the message authentication code, which is shown here inside the opaque field, essentially is computed with a local key that only the ISP knows. So there's no key agreement between any ISP that is necessary. But then the field can only be verified by the ISP itself. Now, we use these opaque fields for the actual forwarding of traffic, which encodes also the ingress and egress interfaces of each autonomous domain. Now, to actually enable recipients to verify the correctness of this information, we also add a digital signature, which is very slow, but anybody can verify it. And then for the actual packet forwarding, we use this extremely fast message authentication code, which can be verified within a few nanoseconds. Actually, on today's Intel, we actually use AES for this message authentication code. And on current Intel processors, it only requires 40 cycles to verify a MAC, which is extremely fast, given a memory access is 200 cycles if it's not in a cache. Right? That's why Scion can actually even be faster for forwarding than a route table lookup, which has to go to main memory. Of course, if it's cached, it's roughly the same speed if it's in level 2 or level 3 cache. But I'll be happy to discuss this offline with you if you have questions. So the important message to take away from this slide is that Scion uses opaque fields that encode the ingress and egress interfaces of the autonomous domains. And that is then checked by the routers in a domain. And that's why the edge routers don't have any routing tables to look up, any intra-domain routing tables, I should say. They may have intra-domain routing tables internally, but there's no more intra-domain routing tables that are necessary in Scion. Intra-ISD communication, of course, also works. It's an intra-domain architecture. And we use also a Scion-level protocol at the top for ISDs to discover each other. And this path then is also encoded in the packet header as well. But ISDs themselves are oftentimes very tightly meshed. So there's usually only one or at most two hops to get from one isolation domain core to another isolation domain. If an entity, for example, in C wants to communicate with an entity in I, which would span a different isolation domain, essentially 3 paths are being combined. A red path, the path from ISD 1 to ISD 3, and then the green path to reach I. And so also the lookup will span a different ISD, but essentially it all works out quite intuitively. So what's very important for the efficiency of Cyan is the use of peering links. If you have announcements, for example, going to C, then along this red path here, the ISPB may announce its peering link to E in this path announcement. And also the ISPE may do the same in the blue beacon going to ADF. And so if C wants to communicate with F, it can take a shortcut, even though the paths, the red path and the blue path, only intersect in the ISD core, they can actually make use of the peering link to go directly from C to B to E to F. Now, this is even possible for peering links that span different ISDs. And essentially, this enables very short paths in Cyan. What's important is that the source always knows what's happening to their packets. So if F sends a packet to I across its peering link, it knows precisely where its isolation domain is being left, and the isolation domain 3 is being entered. So that is very transparent to the source, but these peering links enable very short paths. Essentially, Cyan achieves the same path length and finds all the BGP paths that BGP is establishing, but BGP is using a lot more effort to discover these paths. Now, link failures also are handled quite differently. So first of all, a source would always use multipath communication so if there's a link failure, another path hopefully will still function. But also path construction beacons are constantly sent. And also we send link withdrawal messages that very quickly reestablish paths if there's a link failure somewhere in the network. So everything I've talked about and more is fully implemented. We're already done with the 4th generation of the Cyan code. We've just re-implemented this summer the entire C implementation re-implemented into Python to make it much easier for other people to use. We've also implemented a high-speed router which can switch 120 gigabits per second on an off-the-shelf PC, which is very fast. And our Cyan switch only uses about 120 cycles per packet to process each packet. And the corresponding IP processing required about 190 cycles. So that's on the softer router, Cyan was actually faster than IP. So I added up all the effort we've already spent on this project, and it came up to about 50 person years of effort that with different collaborators and my group spent on this project over the past 6 years. We have a growing testbed also, and we're looking for additional nodes. So if people are willing to run a Cyan router, come talk to me, and we'll be happy to also share the code with you and enable you to run a Cyan router. We're currently also implementing a Planet Lab-like environment where different people can then run experiments on this testbed. I'm not going to go through the entire packet header. I'll just show how it looks like. Essentially, some of the nice features is that the common header is only 8 bytes that really every packet must have, and everything else is optional. Even the source and destination address is optional. They're also variable size. They may not even be present because the Cyan router doesn't look at the destination address. Right? So you actually don't even need the destination address. And it also enables, it has a lot of features. For example, the source could be an IPv6 address and the destination could be a MAC address or vice versa. Right? It's very flexible in this sense. And we've defined a number also of extensions, some of which I'll briefly discuss in a couple of minutes. So let me briefly talk about a few of the security applications we're able to build on this architecture. And I'll first talk about the root of trust management, and then some of the applications that benefit from packet carried forwarding state. So let me first talk about the trust root management, and I'll best explain this based on a picture. But essentially, each ISD, each isolation domain manages their own roots of trust, and there's a trust root configuration file that serves as the main root of trust for an isolation domain. So here I'm showing an example of the EU ISD core, for example, and then we see the Swiss ISD next to it. So we have this trust root configuration file, which contains the name as well as a version number, and then a number of root certificates that are important for this and that can digitally sign these trust root configuration files. So here we see one that has 3 ISPs, A, B, and C, and then also certification authority, CA1, which these 4 entities would form the main roots of trust for this ISD. And then, very important, is an update policy that specifies how many of these signatures are needed to update and change this TRC file. And so here the policy says at least 2 signatures are needed. And then we see the signatures of the previous version TRC file used to sign this TRC file. Then we also have AD level certificates. We see one that's signed by ISP-A, with the private key of ISP-A, and then also the Swiss ISD TRC file that's again signed by A. So all the ISDs would cross-sign each other's TRC files. Now what's really nice about this is it becomes very explicit what needs to be trusted, and also updating these TRC files becomes very simple. Because what we do is when we send out a beacon message, the beacon message, which floods the whole network, contains a version number of this ISD file. And if a beacon is being sent with a new ISD version number, immediately each ISP that receives it asks upstream and says, give me the TRC file with the new version. And it can immediately be verified. And then as the beacon message traverses the network, very quickly everyone obtains a new certificate or obtains a new TRC file. And compare this case with DigiNotar. When DigiNotar became compromised, it took weeks to revoke the public key of DigiNotar. In this scenario, it would take maybe 1 minute, and the whole network would be updated. And what's important is actually that the network should contain a mechanism that enables efficient certificate update and revocation. Because to operate the network correctly, we do need certificates, right? We need certificates for TLS, we need certificates for DNS, we need certificates for BGP-SEC. But these networks don't contain, today's networks don't contain good mechanisms how these roots of trust are being updated. And if the network would contain it, then we'd have a much stronger primitive. I'll be happy to also discuss RPKI with you. It actually turns out that RPKI introduces circular dependencies between routing and the update and revocation of certificates. And that's exactly something you don't want to occur, right? So you don't want that the certificate mechanism depends on routing, and that the routing mechanism depends on the certificates, right? Because you could not reboot the network securely. But anyway, in Cyan, we've done this very cleanly and really built in this certificate update mechanism into the routing protocol. Now, next, I'll briefly want to talk about packet carried forwarding state, which is something we make use of a lot. The observation is that per flow state on routers can cause many different issues. So Schuchard et al. At University of Minnesota have nicely shown that today's routers are very vulnerable to state exhaustion attacks. They can actually bring down with their attacks the internet based on selectively using state exhaustion attacks on different routers in the network. And as a security person, whenever I look at a protocol that has state somewhere on a router, immediately a light bulb goes up and says, okay, this could be a vulnerability. And so in all the mechanisms we've designed in Cyan, we're very careful that there's no per flow state in the fast path of a router. This makes the construction of a router much simpler, but also prevents a lot of these types of attacks that attack the state or attack inconsistencies of state at different routers. In fact, if you have state inconsistencies in routing tables, you end up with routing loops, and that's exactly why we have TTLs in today's packets. Right? If we wouldn't have any inconsistencies in forwarding tables, we would not need TTLs, time to live fields. And so in Cyan, we don't need a TTL field because there cannot be a loop in the network. And so one of the mantras we're using in our research is no per flow state in the fast path, and all our systems are built based on that. So I won't be able, unfortunately, to go into the details of the different mechanisms we're able to build based on these mechanisms, but we have papers on this. So there's one called Lightweight Anonymity and Privacy called LAP for high-speed anonymous communication. It's not as anonymous as Tor, but it pretty much has zero overhead for the network, for the packet forwarding, and it provides a property that we call topological anonymity. Then we have a DDoS defense mechanism that's called STRIDE, a path validation mechanism called OPT, or also a mechanism for fault localization and multipath forwarding. A lot of people, I'm sure, are wondering about incremental deployment because it's obviously, the internet is working, and so you say, well, if this is requiring a lot of effort, nobody's going to use it. Well, fortunately, Cyan is very lightweight to deploy. An ISP, all it needs to do is install a few Cyan edge routers, and then install an additional server somewhere in the network that handles implements a beacon server, certificate server, and path server, which is very inexpensive commodity hardware. And internally, the standard MPLS, IP, or SDN forwarding can operate as it's operating today. Then, if different ISPs are not directly neighboring that deploy Cyan, we establish IP tunnels. And this is exactly what we do in our testbed. We have a number of IP tunnels connecting the different deployments. End domains also have very minor changes. You can, again, use IP routing internally. So we use IP headers for layer 2 forwarding, essentially. So a Cyan host would add the Cyan header and another IP header just to get it to the edge router or to send by an IP tunnel to the first Cyan router. Then that router would remove the IP header again. So it's really, we're using it as a layer 2 protocol. So incremental deployment is actually quite feasible. And we've helped this with a project that we called simply the Box project, where we've implemented a hardware box with 2 Ethernet interfaces that if we have, say, a smart meter in ADF and the controller station ADI, that we can put simply this box between the smart meter and its wherever it gets plugged in, and also between I and the controller station. And it transparently uses Cyan to communicate. So the boxes detect each other. We're using some tricks to make sure they don't send any extra packets to detect each other, because we don't want to disrupt any of the endpoints that may not understand these Cyan discovery packets if we'd add special packets. So once the boxes detect each other, they then set up multiple Cyan paths between each other, and then they simply monitor the regular IP packets. So they don't do anything to the actual packets initially, but if they detect that the connection failed and some of these IP packets don't get through anymore, the boxes repackage the packets in Cyan packets, send it through the network, and encapsulate and then decapsulate at the destination. So essentially, the end hosts do not need to be updated. So you can have a commodity smart meter, commodity monitoring station, and without any updates, make use of the Cyan network for as a fallback network in case the real internet is failing. And in our experiments, we've run this the whole summer. We've actually noticed a lot of failures, and for each IP level failure, the Cyan network actually did operate correctly. Of course, the Cyan network also has outages. If links go down, you have a brief outage, but because of the multipath aspects, there is never an actual outage, and it can also quickly heal, as I've described. So in summary, SAN proposes a complete redesign of a network architecture that resolves a lot of fundamental problems with BGP. So all the BGP protocol convergence issues, which are actually also a big problem from a security perspective, that all these issues simply go away. Also, the separation of the control and data plane offers for very powerful mechanisms. And also the isolation of mutually untrusted control planes turns out to be exceedingly useful. Path control can be done by ISPs as well as senders and receivers. Routers become very simple. And the root of trust is also selectable by the isolation domain. So India can run and define their own isolation domain. China, see some people from China, can run their own isolation domain and select their own roots of trust for their own domain. So what's important is, again, I want to emphasize, SAN is only an isolation architecture only for the control plane. For the actual data plane, it's a transparency architecture. It doesn't prevent anyone from communicating with anyone else, but it provides simply more information about how your packets are flowing through the network. So I could go through all the stakeholders' pros and cons, but let me not do this and simply conclude now that I believe that a new internet architecture's deployment is actually necessary to resolve a lot of the problems we have today, and it's also possible. It's a lot easier than we initially thought it would be. And so our idea is to really provide strong incentives and strong properties that provide high values for ISPs to deploy. And also this alternative architecture can be easily run in parallel with the current architecture. That's why it's so easy to deploy this. But of course, it requires a community effort to really take the next step, right? We've had the initial ideas, but it really takes a lot of people, corporations, researchers to develop all the standards to make this a reality. And so I hope with SAN we're able to propose an initial architecture for highly secure and available point-to-point communication. So with that, I also want to thank all the team members. And here you see Radha, actually, he was supposed to come. He was visiting our workshop that we had. Every year we have a SAN workshop in the Swiss mountains. And this shows a picture from last year's workshop. And this is a picture of the actual team of my group at ETH at our Christmas dinner with the Zurich Christmas lights in the background. And with that, thank you for your attention, and I'll be happy to answer your questions. Could also be a possibility. Even these isolation domains can intersect. AD can be multiple isolation domains. Essentially what Cyan is doing is it's giving more information. It's essentially giving precise information about who needs to be trusted and which paths packets take. And so this isolation is really only at the control plane level. In that beacon messages from one isolation domain would never go into another isolation domain. So you have some level of isolation for the control plane, and that's the main purpose.
Okay, thank you. Very nice work.
Thank you.
A couple of questions. One is a specific question. So you talked about the oligarchy model,
Right.
and the problem that revocation is complex because the browser and the OS needs modification and so on.
Right.
The question is, why can't you just have a level of indirection, a revocation server that you could consult to deal with that problem? That's sort of my question.
That's a very good question. So why can't we simply have a revocation server with revocation lists? And that's definitely already done. But it turns out there are a lot of issues. Let me see where to start. One big aspect is which revocation server would be for which countries. Let's say India, China, Europe, US all have their own environments. It still wouldn't solve the problem of, some attacker in Malta to hijack the Indian bank's certificate. Right? You're still not solving that problem.
No, I was specifically referring to the problem of requiring a software update. You can avoid that by building into your software a mechanism to consult a revocation server.
So specifically for the routing, I mostly I'll be happy to discuss this more with you about the actual service authentication, but for the routing, revocation servers don't work. Because when you're receiving the routing message, you don't want to rely on routing to reach the revocation server. So actually one thing we've discovered is we have completely different systems that we're using for the routing PKI and for the PKI for end hosts, like for servers. Now for revocation for actual servers, checking, the question then becomes, I mean, revocation is a very old problem, right? And everybody agrees that there is no good solution. If you look at OCSP, the problem with OCSP is that, and that was nicely documented in a nice paper where they showed that OCSP required about 300 milliseconds of extra overhead. I think the median was 300 milliseconds for verifying with the server. And nobody can use 300 milliseconds, right, for SSL connection establishment. So then what they said is, well, let's use OCSP stapling, right, where the server, the web server already staples the OCSP response to at the initial SSL handshake. Now the problem with that is that you still have the same problem with hijacking, right? If in the oligarchy model, if any CA gets compromised, they can still provide you a correct certificate, right? So you're back to square one. It's a very multifaceted, complicated environment.
So my broader question, the second question is a broader one, which is, you yourself listed a bunch of new internet architectures been proposed over the years.
Right.
And at least to me it seems, and perhaps you'll agree, that most of them have not gone anywhere in terms of actual impact. And perhaps the reason is that you really need to meet a very high bar to actually change the internet in any meaningful way. And that high bar really involves identifying a pain point that is sufficiently severe that people are willing to deploy something new. So what, in your view, is such a pain point that might lead people to actually consider something like this?
Right. That's also an excellent question. I think the different internet architectures you said have not gone anywhere. I would rephrase this by they haven't been widely deployed yet. Because I think from a pure research perspective, it's very important to first figure out, how should we redesign a network architecture from scratch. So for example, we also learned, like there's related work like Nimrod that also had different domains as well. And so we definitely learned from other architectures to design ours. I'm hoping that if people develop new architectures, they would also learn from the lessons we've learned in Scion to deploy. Now, what are the specific pain points why somebody wants to deploy this? And what I've noticed is so far I go to talk to a lot of ISPs and everybody gets excited about something else. So one ISP got very excited and actually are thinking about deploying this from the perspective of the isolation. So when you send a packet, you have a guarantee that this packet doesn't go somewhere. Right? Like that early slide I showed, the packet went to London and Belarus and all these places. In Scion, when you send a packet, you get a guarantee that this packet will not leave India. Right? That's a very strong, powerful property. And people say, well, an ISP can also provide this if they have the right BGP filters. Then my next question is, how do you guarantee that all the configurations are correct? And the answer is you cannot guarantee it, right? You may have today the correct configuration. Now tomorrow, you hire a new sysadmin and some mistake happens, and suddenly the packet goes out, right? So to really provide a strong guarantee, we can do this in Scion. You cannot do this in today's internet. Another pain point is the availability itself. In today's internet, you have these routing changes that can just happen. And so you can never really get strong availability. But in Scion, you can, right? And if the control plane and the data plane are completely separate, so the data plane can operate even if the control plane goes haywire. Right? That has been, and also the DDoS, we have very powerful DDoS defenses that currently another ISP is thinking about deploying in their network. So the business model would be that an ISP can, with Scion, provide interdomain SLA guarantees, because the way the paths are being composed, the SLAs can also be composed in the way, unfortunately I wasn't able to explain this, but they're thinking about developing a product based on that. So they could provide kind of dynamic leased lines, on demand without really making a lot of configuration. So that's another business model. Another ISP really liked the fact about the control, so that the receivers and senders have very good control over how the packets are flowing. That's what they like the most. Others like people who like security, they like our certificate infrastructure aspects. And they say, well, we can actually, I haven't been able to explain this, but we have these ARP key extensions where we have a mathematical proof that at least 3 trusted entities have to be compromised in order to compromise a server. So we can go to UBS or Credit Suisse, the big Swiss banks, or some Indian bank, and we can say, only if all these 3 entities are compromised, somebody can play man-in-the-middle attack on your domain. And we have a mathematical guarantee that this is the case. So the whole thing has been model checked. And some people like that part. And I talked to, so another question I think somebody may ask is to say, well, countries who want to control their citizens' communications, right, they would love SAN because SAN looks great for censorship. That's actually not the case. Because the sender knows exactly how in SAN the packet flows, you cannot use the control plane to now reroute packets. Right? And so actually, I talked to the Tor guys about this because they came to me and said, well, I think SAN is no good because it would make Tor worse. But actually then after discussion, well, it took 1 hour, they realized that SAN would actually provide an advantage to Tor. And especially the encrypted paths that we provide has this. So they were a little bit worried, though, that SAN may be misused in a way we cannot anticipate yet. But they agreed to the way it's presented today. The way we envision it, it would actually be better for citizens, and it would be more difficult to inflict censorship. So this is a lot of different aspects.
Okay, can we take one quick short question? You can do it after. Go ahead.
Very interesting talk. So, with respect to path validation, couldn't it be possible to enable the record route option in IP to trace the route that the packet could take? I know that this could probably introduce some additional processing overhead because this packet will have to take the slow path in routers, right?
That's a very good point. So we had a paper this year at SICOM to exactly address this problem where we do path validation that is so fast that there's pretty much 0 overhead. Right? So we can do it in as little as 10 bytes per packet, and the recipient can verify that the packet truly went through all these ISPs. And the trick is to use the super fast AES function. Now you may wonder, how do we derive the key? Because the router needs to have a different key for each destination. So we use another trick where the router first uses AES to derive the key that is then shared with the destination dynamically based on the packet. Then it uses that key to compute the MAC. And because the MAC, this computation only takes 40 cycles, it's exceedingly fast. And pretty much, we were able to do this at pretty much no overhead. That's our SICOM paper system called OPT.
Thanks.
So it's, like, again, no per flow state on the fast path. That's the important mantra. Great.
Okay, and I believe Adrian will be available to take more questions offline. That was a wonderful talk. On behalf of the organizing committee, we would like to present a couple tokens of appreciation to Adrian.
Okay. Great. Thank you. Wow. It's really beautiful.
Thank you.
Great. Wow. It even has a security code.
Yeah, it has. Okay, one quick announcement. We are running a little behind schedule, which is okay. We have coffee and tea break until 11:30, but